Okay, so my name's Jaden Mormon, and I'm here to describe the relation between pressure and temperature as it varies with altitude. So to start off, we're going to assume that we have an ideal gas. This allows us to use the ideal gas law right here. Second off, we're going to assume that the system is isentropic, which means that there's not going to be a change in temperature, and that the process is reversible. And third off, we're assuming that we are only using 1 mole because this allows us to neglect the end term in the ideal gas law. So, starting off, we have the basic equation of statics, which essentially says that dP over dz is equal to negative rho g, where rho is the density of the gas. And then we have PV equals RT, which is the ideal gas law. Pressure times volume equals equals the ideal gas constant times the temperature. Then we have du equals the change in heat, delta Q minus PdV. And then we have Cv equals dQ over dt, where Cv is the heat capacity at a constant volume, and then Cp is the heat capacity at a constant pressure, equals Cv plus R. So, moving on. We have that we're going to start off with this equation, dP over dz equals, and we're going to rewrite it a little bit using the ideal gas law. So we're going to have mP over RT is equal to, where m is the mass and P is the pressure, times G. And this is really nice because we're able to rewrite it, and we can get all of our variables on the left side and all of our constants on the right side, which is going to make it a lot easier to derivate. So we have T over P, or to integrate. T over P dP is equal to negative M over R G dz. So this is nice because we can just integrate from P1 to P2 on this side, Z1 to Z2 on this side, and then we get, I'm going to carry this down because we can't quite solve this one yet, but we can solve this, and this is going to be equal to negative mg dz over r. Pretty simple. So this equation here with this carried down is, we're going to leave this be, but that's a pretty simple starting point. Second thing we're going to do is we're going to mess around a little bit with this equation. du equals delta Q, a little bit of change in heat, P du. So delta Q is actually going to go off to 0 because we said it's adiabatic. There is not a change in temperature. So we can just cross this term out and neglect it. But the du, so that means that du is actually just equal to P negative P dV. P we can replace using this, so we get du is equal to RT over V dV. And then we can actually rewrite du as Cv dt is equal to RT over V dV. We can rewrite this just, or negative RT, carry down the negatives. And then we write this just a little bit more, and then we get Cu times the integral of dt over t is equal to negative r times the integral of dv over v. Simple integral. Then this is from t1 to t2. This is from v1 to v2. Pretty simple integral to solve. We pretty much just get that Cv times the natural log t2 over t1 is equal to negative r times the natural log of v2 over v1. And then we can divide this over, and we'll get that the natural log of t2 over t1 is equal to is equal to the natural log of v2 over v1 to the negative r over cv. And so then we raise both sides to the power of e, and we get t over t1 is equal to v over v1 quantity negative r over cv we're going to bring this up. And so this is nice because we got rid of the natural logs. And then we can actually substitute in again using the ideal gas law. So we're going to have T over T1 on this side still is equal to R. So we're substituting this in for the V here. It'll be a little bit more helpful, but we'll have RT over or T1 over, or no, just RT, sorry. RT over P over RT1 over P1 raised to the negative C or R over CV. Cancel out the R's, but the temperatures and the pressures are different, so we can't cancel those out, unfortunately. But this will allow us to once again rewrite it to a better form, which will give us T over T1 times P over P1, or P1 over P, quantity to the negative R over CV. And then if you look at this, you're actually able to rewrite it again, which will give us T over T1 to the negative R over CV plus 1 equals P over, or P1 over P negative R over CV. And then real quickly, we can define negative R over CV actually equal to CV plus 1. And then we can take that, define that as gamma. And so that's because of this. And that is pretty useful because we can then go T over T1 raised to the gamma power is equal to P1 over P raised to the gamma minus 1 power. And then, so the final step we can do here, or another step we can do here to make it look a little better, is we can say T is actually equal to T1 times P1 over P raised to the gamma minus 1 over gamma power, because we just raised this side to the 1 over gamma times 1 over gamma, so that cancels out, but this doesn't. And then we can real quickly consolidate these two before we move on. And so we're going to have, so we have this equation here, and T equals T1 P1 over P to the gamma minus 1 over gamma. And so now we have something for T. And so I'm going to write down one equation that we're going to bring with us into the next step. And then I'm going to erase the whiteboard and have some more space to finish it off. But it's going to be that from P1 to P2, we actually substitute in this T for the negative mg dz over r. And so this is then going to result in, from P1 to P2, it's going to be T1 times P1 over P gamma minus 1 over gamma. Sorry, that's a bit messy. Gamma minus 1 over gamma over P dP is equal to negative mg dz over r. So this is what I'm going to leave for now. And then we're going to move on a little, and then I'm going to erase all this so that I can finish out the problem. But this is the important thing that we've done. So to finish this off, the first thing we're actually going to do is we're going to mess with this just a little bit more. So we're going to recognize that T1 and P1 are actually here are both constants. So we can pretty easily pull them out of the integral by just doing a little bit of basic algebra. And then we get P1 to P2 of P to the gamma minus 1 over gamma over P. So the nice thing about this is that we can then multiply it over to this side, mg dz over r. So this gives us P1 to P2, P to gamma minus 1 over gamma over P equals negative mg dz over RT1. And this is also multiplied by the P times gamma, P1, gamma minus 1 over gamma. Because we just flip the exponent again once it gets to the other side. It's a pretty simple concept. And then we can carry this on. Just to quickly solve this, it's going to give us P2 to the gamma minus 1 over gamma minus P1 gamma minus 1 over gamma over gamma minus 1 over gamma. And this side's going to stay the same. And then we're actually going to multiply this over. So this is going to give us P2 to the gamma minus 1 over gamma minus P1 to the gamma minus 1 over gamma is equal to negative mg dz over RT1 gamma, because we're just multiplying this over. Or it's probably easier to RT1 times P1 to the gamma minus 1 over gamma times gamma minus 1 over gamma. It's a pretty daunting equation, but we're going to move this up here real quickly so we don't run out of any more space. So, and then we can see that if we add this over, it'll actually help us simplify a lot of this pretty easily. And so it's going to give us the term P2, gamma minus 1 over gamma, is equal to negative mg dz over RT. Yeah, over RT times gamma minus 1 over gamma plus 1. And this is because we're just able to add this over and then divide out these terms, which is pretty helpful again. And so we pull out the term P1 to the side here, to the gamma minus 1 over gamma. And then because that's thing that's multiplying all of it, we're able to cancel out these terms. And so then we actually just get that it's equal to P2 is equal to, or the final pressure, P2, whatever the pressure we're looking for, is equal to P1 times 1 minus mg dz over RT to the gamma minus 1 over gamma. And then in order to get rid of these, we had to raise this to the power of gamma over gamma minus 1. So it's going to be raised to that power. So this is the equation for pressure. And then it's pretty simple. We just take this equation that we derived earlier, and we substitute it in, and then we get that T2, or T, the temperature that we're looking for, the final temperature, is going to be equal to 1 minus mg dz over RT1. And then that quantity is going to be multiplied by gamma minus 1 over gamma. And then, and then you add in some brackets here to keep it nice and stable. And so these are the two equations we looked for. We have the final pressure stated in terms of two changing variables, pressure 1, temperature, and then the change in altitude. So the three things that we are looking at changing. And then we also have temperature stated in two changing variables, that being the change in dz. And so this will actually give us correct answer, and this is the final equations. So